In this video, I'm going to go through the inference review packet for every single test and interval you might encounter on the AP exam and just show you what conditions you need to check and what the mechanics would look like. So we're going to start with proportions. We have one sample and we're trying to construct a confidence interval. So the conditions I would need to check would be independence, random, 10%, and success failure because it's categorical variable and not quantitative. All right, the name of this would be a one proportion Z interval, and the mechanics would look like this. I'm going to take my statistic 0.74 plus or minus. I need my critical Z value for 98% confidence. I'm going to inverse norm 0.99, or I can do inverse norm 0.01. Either way, I'm taking the positive value of 2.33 times my standard error, which is 0.74 times 0.26 over the sample size 1,644. All right, so I'm going to go to my calculator and I'm going to go to stat test. I'm going to find one proportion Z interval. X is the number of successes, so I have 74% of my sample size. But remember, this has to be an integer value, so I'm going to round this to the nearest integer, 1,217. My sample size is 1,644, and my confidence level 0.98. Calculate. So 0.715 to 0.765. 0.715, 0.765. And then I would obviously need to write a conclusion there. All right, let's look at the next question. Okay, now what we want to know is there statistical evidence that her school is different. We have one proportion, one variable, one sample. So this is going to be a one proportion Z test. So going through this, my conditions are going to be exactly the same as they were. Independence, random, 10%, and success fail. The mechanics of this, they believe 60% of students earned a 3 or higher. So that is my population parameter, my claim, not 0.3 but 0.6. A sample was done and 65% earned a 3 or higher. So that's my sample statistic. So calculating a z-score, it's going to be the statistic minus the mean over the standard deviation. The reason the standard deviation is I do know p, it's 0.6. So 0.6 times 0.4 divided by my sample size of 54 is going to give me a z-score. So let's get that from the calculator. Stat test, one proportion Z test. The null is 0.6. The number of successes, so this is 0.65, 65% of the 54 students earned a 3 or higher. Again, this needs to be an integer. Round that to the nearest integer, which is 35. Sample size is 54. The alternative, she wanted to know, is there evidence that her school is different? Implying a two-tailed test, and calculate. So there's my test statistic, there's my p-value, 0.722. So my z-score here is 0.722, and to get my p-value, I have the probability that z is greater than 0.722 is equal to 0.470. So about a 47% chance. So we'd fail to reject the null. There's weak evidence. Okay, moving on, taking a look at the next question. Now we're moving on to two sample. So in this example we're taking a look at, we have a 2-sample confidence interval. And I can see here this is categorical. They're voting for him or they're not. So it's categorical. It's either chi-squared or the z distribution. I have one variable that I'm measuring, who you're voting for, and I have 2 samples, men and women. So this becomes a 2-proportion z interval. So conditions I need to check are random, independence, 10%, success failure, and the new one, because I do have 2 samples, is independent group. Okay, keep in mind you need to check the 10% condition for both samples, and you need to check the success failure condition for both samples, ensuring the number of successes and failures for each group is greater than or equal to 10. So provided those conditions are met, this is going to be a 2-proportion z interval, which we're going to do. The mechanics are going to look like this. I can do the male minus the female or vice versa. Male is 0.52 minus the female percentage was 0.45 plus or minus my critical value for 95% confidence, inverse norm of 0.975 or 0.025, so 1.96 is my critical value, times my standard error. Now you'll remember for 2-proportion z interval, we're not pooling. We're assuming that these are different proportions. So I'm going to have the male percentage 0.52 times 0.48 divided by that sample size, 473, plus female 0.45 times 0.55 divided by 522 for my standard error. In the calculator, we're going to go to 2-proportion z interval. There we go. x1, that's the number of successes from the male group, so 0.52 times 473. This needs to be an integer, so that's going to round to 246. The sample size was 473. For the females, 45% times 522. Round that to the nearest integer, 235. Sample size 522. And the confidence level for this question was 95%. Calculate. So 0.008.132 if I'm rounding to the nearest thousandth. On the AP exam, just leave all the decimals, don't worry about rounding it. 0.132. So then I would obviously write a conclusion for that. So let's take a look at that 2-proportion z test. And this is a special test that you really need to remember because this is the only test for which we need to pool. So I have categorical variables, a variable. Basically, they're asking, are these men comfortable talking about their problems or not? So I have a categorical variable. I have 2 groups. I have young men and older men. I have just the one variable, multiple samples. Is there statistical evidence, meaning this is a test? So it's going to be independence assumption I need to check, randomization, 10% for both groups, success failure for both groups, so you'll end up with 4 numbers here, 2 successes and 2 failures from each group, and then independent groups. All right, each sample needs to be independent. So when I'm doing my test, the null would be if I use subscripts Y for young men and O for older men, that I believe the difference is 0. And they want to know, is there evidence to support the magazine's interpretation? They said that young men were more comfortable sharing. So the proportion of young men sharing their problems was going to be greater than the old, greater than 0. So that would be the null, that would be the alternative. Okay, so once I get into the mechanics here, so my population parameters, I'm claiming their difference is 0. My sample statistic is going to be young minus old, so 80 out of 129 for the young, minus 98 divided by 184 for the old. So doing quick calculation, that's going to give you 0.088 is the difference. Since I'm pooling, I believe that these are the same, these two proportions. So I'm going to come up with one pooled estimate. So I'm going to take the total number of successes divided by the total sample size to get this pooled estimate. Calculating that. I get 0.569. All right, so taking this information and calculating a z-score now, I would have z equals my statistic. Well, that's the difference between the two proportions, 0.088 minus my mean, which I'm claiming is 0, but they're the same, over my standard error pooled, which is going to incorporate this 0.569 times the complement, 1 minus that, 0.431. The sample size for the young men was 129, plus for the old men, 0.569 times 0.431 divided by 184. There's my pooled estimate. All right, so to the calculator, I'm going to go to two proportion z-test. Number of successes from each group, 80 young men shared their problems out of 129. For group 2, 98 out of 184. And this was a one-tailed, upper-tailed test. And calculate. So I have a z-score of 1.54 and a p-value of 0.061 or 0.062. 1.539. And the probability z is greater than that is 0.062. So at a 5% level of significance, I'm going to fail to reject and all there's weak evidence. Okay, let's move on and take a look at the last part of categorical variable inference, and that's goodness of fit. That is when you have one variable and one sample. And the difference here, why you're not going to use the normal model, is because you have more than two categories. In this case, we have attacks on women, and this is a question that I think we did in class or for homework, using guns, knives, weapons, and personal attacks. So is there evidence? Okay, this is definitely a categorical variable. I have different categories here. So it's either z or chi-squared. I have one variable, the variable how were these women murdered, and then one sample. And evidence tells me it's a test. Chi-squared does not have any confidence intervals, so at that point, once you identify as chi-squared, it's going to be a test. I have three conditions to check. I have the random condition, I have the counted data, and I have the expected cell frequency condition. Okay, so at this point, I can name the test. So my degrees of freedom for goodness of fit test are n-1, where n is the number of categories. So I have guns, knives, other weapons, and personal attacks. So I have 4 categories minus 1, 3. And the name of this test would be a chi-squared goodness of fit test. On the AP exam, we'd expect that you write out goodness of fit as opposed to using the acronym there. Okay, so getting into the mechanics here, I need to know my observed values and my expected values. Well, my observed values are here. So I have observed, and I have guns, knives, other, and personal attack. 372 by knives, 344 by 158 other, and 344 personal attacks. my expected. So I want to figure out what the total is, and they tell me in the stem of the problem. There was a weapon identified in 2013 of them, so it's going to be 2013 is my total. So I expect 63.4% of 2013 to be killed with guns. So 0.634 times 2013 is 1276.242. And I'm just going to not show these other calculations. I'm just going to do them on the side here. So for knives, 0.131 times 2013, 263.703. Other, 0.168 times 2013, 338.184. And personal tax, 0.067 times 2013. Okay, so those are my expected counts. And for my test statistic, I need to do observed minus expected squared divided by expected. And some of you had the test in your calculator, and you can do it in your calculator. I'm going to show this out by hand in case you don't. Observed minus expected squared divided by expected. So I'm going to go to the calculator and create some lists and have the calculator do the work for me. So in list 1, I'm going to put my observed counts, which are 1139, 372, 158, and 344. Expected, I'm just going to enter my expected counts, 263.703, 338.184, and 134.871. Now, list 3, I'm going to put the test statistic, which is observed L1 minus expected L2 squared divided by expected L2. And that formula's on your green sheet. Okay, so I can see by far the murders by personal attack contribute to the chi-square test statistic way more than anything else. I need to sum up this list, so I can go to the catalog, go down to T, arrow up to sum list 3. So that's my test statistic, 479.507. I'll come back to that in a minute. All right, the observed minus the expected, that's list 3. I had, kind of shift this down a little bit, 14.758, 44.475, 96.002, and 324.27. And the sum is chi-squared sub 3 equals 479.508. Okay, so I need to get a p-value based on that. So the probability that chi-squared sub 3 is greater than that. I'm going to need to use chi-squared CDF. Second distribution, chi-squared CDF is choice 8. I'm going to put in my lower bound, which I can take that answer, comma 999, and then my degrees of freedom, 3. Okay, you can see your answer is 0 here. Your p-value is not 0. It's very, 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 very close to 0. So we can say essentially 0. P-value is low, we're going to reject the null. Anytime you reject the null with a chi-squared test, regardless of what test it is, you need to talk about the biggest difference between the observed and the expected. In this case, way more women were killed by personal attacks. We observed 344, but only expected 135. Then that's the biggest contributor to your test statistic, as you can see here. Okay, let's move to the next chi-squared test. Here we have a test for homogeneity, and determining homogeneity is you have one variable with multiple samples. Okay. All right, so we want to know, are there differences in the national origins of cars driven by student and staff? So we have one variable and multiple samples. We did a sample of the student lot and the staff lot and recorded their car type. So same 3 conditions, random, counted data, and expected cell frequency. And they have to be greater than or equal to 5. If not, you need to combine cells to make that happen. So degrees of freedom are the number of rows minus 1. You do not include the totals. So there's 3 minus 1 times the number of columns minus 1, not including the totals. 2 minus 1. So there's 2 degrees of freedom. So you have 3 rows minus 1 times 2 columns minus 1 gives you the 2 degrees of freedom. Official name of the test is chi-squared test of homogeneity. Okay, that would be in your closing statement. Okay, looking at the mechanics of this is where you're going to end up using the matrix in your calculator. So going to the calculator, going to second matrix, we're going to edit matrix A. It's rows by columns, so I have 3 rows, I have 2 columns, and I'm going to input this data here that I have. So for students, 107, staff 105, 33, 12, 55, and 47. Then I'm going to go to stat test and I'm going to run the chi-squared test. My observed values are already in matrix A. I want the expected values to be put in matrix B. Calculate. So I'm going to come back to that in a minute. I want to check out matrix B. So going to matrix B, edit. These are my expected counts. I need to confirm that these are greater than or equal to 5, and they are. So I would need to write these on the table and communicate to my AP reader. I'm going to show you the mechanics now. So what we're going to have is I need to write out 3 formulas at most. So I have my first cell here, 107, minus my expected value, 115.15 squared divided by the expected value, plus my next formula would be 105 minus 96.847 squared divided by that expected value, plus dot dot dot, plus the last formula that we're going to have in the bottom right. Your observed was 47 minus expected 46.596 squared divided by that expected value, 0.596. Okay, when you sum those up, we already have the sum of that. That's going to be your 7.83, giving you a p-value of 0.02 essentially. So this sum is 7.83, and your probability that chi-squared sub 2 is greater than 7.83 is essentially about 2%. Because the p-value is low, you'd reject the null. Again, when you're rejecting the null, you're looking at the biggest discrepancy between the observed and the expected and talking about that in a third sentence. So if I look at matrix B and I look for the biggest discrepancy here, what do we have? It's definitely not from the bottom row. These are about 9 or 10 apart. It looks like more students drive American cars and less students drive European cars than staff. I can see that using these 4 here. So I'd want to state that in the third sentence of my conclusion. Okay, last test for chi-squared is independence. And that's when you have 2 variables and 1 sample. Okay, keywords to look for: association, independent, dependent. Okay, I see that here. Is there an association? So my null would be that gender and party affiliation are independent, and my alternative would be gender and party affiliation are not independent. So conditions are going to be the same: random, counted data, and expected cell frequency. Mechanics are going to be very similar to what they were above. I'm going to plug these into the matrix, getting my values for the expected, so 3 by 3, and my values here, 39, 17, 12, 15, 30, 12, and 30, 31, 16. Go back to chi-squared test. Observed in A, we want expected in B, calculate. You're going to need to go to matrix B, take a look. These are all greater than or equal to 5. I don't need to worry about combining any cells. So my degrees of freedom, I have 3 rows minus 1. I have 3 columns minus 1. 2 times 2, I have 4 degrees of freedom. This is a chi-squared test of independence. And getting to the mechanics, I would have chi squared sub 4 equals my first observed value is 39 minus expected. Looking at matrix B, I'm just going to be referencing this for the next few moments. 28.277 squared divided by expected plus 17 minus 26.257 squared divided by 26.257 plus, running out of the room, plus dot dot dot. The last formula you would need is 16 minus 15.248 squared divided by that expected. Okay, going back to the main screen when I did the test. My chi-squared test statistic, 13.85 with a p-value of 0.01. So this equals 13.85. The probability chi-squared sub 4 is greater than 13.85 is about 0.01. The p-value is low, we would reject the null. Looking at the biggest difference between my observed and my expected values as part of my conclusion. And as I'm taking a look at these, it appears as though the biggest discrepancies, the independents are pretty close. Republicans are fairly close except for that middle one, the top one. Democrats, it looks like I have some differences. It looks like Democrats are more likely to be in the West and Republicans are less likely to be in the West, or Republicans are more likely to be in the Northeast and Democrats less likely. That would be part of my third sentence. Okay, in the next video, I'll talk about what to do when you have quantitative data.